So in our section 3-4, we're going to deal with some more properties involving parallel lines and perpendicular lines. Okay? Now, this first one up here, they don't give it a name, and I really don't like that they don't give it a name. So I am actually going to call this, and actually maybe you can come up with the name of this one, see if you agree with me. But they're saying if A is parallel to B, if line A is parallel to line B, and B is parallel to C, then A is parallel to C. That sounds an awfully lot like something we've already done in here. And that's exactly what I'm going to call this. This is the transitive property of parallel lines. Okay? I will always refer to this as the transitive property of parallel lines. It's a whole lot easier to remember than Theorem 3-7. Okay? So, and again, this should make sense to you. This should make sense to you. If we have two lines that are parallel to each other, A and B, and then we know that line B is also parallel to C, then it kind of just makes sense that A must be parallel to C as well. Okay? Let's look at our next one. Our next one says, if M is perpendicular to T, now again, perpendicular means that they intersect and form a right angle, right? In fact, they intersect and form 4 right angles. But if M is perpendicular to T and N is perpendicular to T, then M is parallel to N. Okay? Then M is parallel to N. And so this one, I'm going to call this doesn't have a really nice name to it, but it's going to be called lines perpendicular to the same line theorem. Lines perpendicular to the same line theorem. Not a real nice name, but again, helps us remember what it says. And so, basically, summarizing what this theorem says, if two lines are perpendicular to the exact same line, then those two lines have to be parallel. Those two lines have to be parallel. And of course they do. I mean, we can walk through a plan for the proof for this real quick. Okay? If I know that M is perpendicular to T and N is perpendicular to T, again, I said perpendicular means they intersect and form a right angle. Okay? Well, then I know that this angle, now if I was writing an actual proof, I'd have to start naming stuff, okay? But I know this angle is a right angle then, and I know this angle is a right angle, okay? If I'm given this, I then know I have two right angles. We have a right angle congruence theorem that says that all right angles are congruent, so therefore I know these two angles are congruent. Well, those two angles happen to be corresponding angles. And so then by the converse of the corresponding angles postulate, I then know that these two lines have to be parallel. Okay? So again, this is why we should like theorems, because theorems actually shortcut our work quite a bit when we're trying to work with proofs. Okay? All right. So let's take a look here. In fact, we happen to have a proof here that we can write of what I just said. All right, I just walked us through this proof, so let's see if we can recreate it. So we want a 2-column proof. Remember, they have to have statement and reason for our 2 columns. And our givens are always our first statement. So we have R is perpendicular to T. Oops. And S is perpendicular to T. Nope, because we are trying to prove that theorem. And so since we're proving that theorem, we can't use that theorem in our proof. Okay? That would be like trying to define the word sticky. Something is sticky if it's sticky. You can't do that. Right? Okay. Where do we go from here? Well, again, what does it mean to have perpendicular lines? They intersect and form right angles. So that means angle 1 is a right angle. Is there another right angle in this diagram? Which one? Angle 2. Angle 2 is a right angle. All right, this is from the definition of perpendicular lines. Okay, well, I know I have 2 right angles. So then what do I know about those? I know that right angles are congruent. I know angle 1 is congruent to angle 2. And that, if you look back in your notes to section, I believe it's 2.6. If you look back at your 2.6 notes on the back side, again, I believe it's on the back side, 2.6 notes. It's all Unit 2 notes. So you should be your Unit 2 packet. Back side of your 2.6 notes, there is a theorem there that I called the right angle congruence theorem. The back side of your 2.6 notes. And that theorem simply says all right angles are congruent. Back side of your 2.6 notes. Okay, so we now know that angle 1 is congruent to angle 2. Well, what type of angle pair are those? They're corresponding angles. And so since corresponding angles are congruent, what can I say? R is parallel to S. And why is that? What theorem or postulate tells me that? Careful. Careful. It is not the corresponding angles postulate. You're going to be real mad when I tell you the answer. It's not the corresponding angles postulate. What was that? The converse of the corresponding angles postulate. Those are 2 separate postulates. Okay? The corresponding angles postulate says if lines are parallel, then angles are congruent. But the converse of the corresponding angles postulate says if angles are congruent, then lines are parallel. We've got to make sure we're using the proper one. Okay, and there's our proof. Good work. Questions? No questions? Okay. Then, moving right along here, let's take a look down here. We have something called the perpendicular transversal theorem. the perpendicular transversal theorem, says if n is perpendicular to L and L is parallel to M, then n is perpendicular to M. Again, we could walk through a proof on this one real quick because we know that n is perpendicular to L. So this makes a right angle since they're perpendicular. We have a parallel line here and a parallel line there. That means this angle and this corresponding angle must be congruent because we already have parallel lines. Well, again, if this is a right angle, then this must be a right angle. And if this guy's a right angle, that means that this line, N, must be perpendicular to this line, M. Okay, so we can kind of walk through that proof for showing that. All right, so there's our 3 new theorems. Let's take a look at this problem here. Solving problems with parallel lines. Can you assemble the pieces at the right, or actually below here, to form a picture frame with opposite sides parallel? All right, so picture these as pieces of wood. Okay, so we have pieces of wood here, and on these pieces of wood, these angles are 60 degrees, and these angles are 30 degrees. So do we have these appropriately cut so that when we assemble our picture frame, the opposite sides are actually parallel? So if I assemble this like this, will my opposite sides actually be parallel? Will it be a nice looking picture frame, or will it be kind of wonky? What do you think? How do you suppose we're supposed to figure this out? Let me give you a hint. What shape are picture frames? Not always squares, but rectangles. Most of the time, right? Unless we're talking about some kind of fancy frame. But yeah, most of the time they're going to be rectangles. Okay, what do we know about the opposite sides of a rectangle from previous knowledge? They should be parallel. They should be the same length. Okay, good. What do we know about the angles in a rectangle? They are what kind of angles? Right angles. They should be, in a right angle measures what? 90 degrees. So in a rectangle, we should have 4 90-degree angles. So then the question is there a way to put these blocks together so that we get nice 90-degree angles? Hello? Yes? No? Maybe? How do we think? Which ones are we going to put on the sides? The ones with the 60-degree angles, or the ones with the 30-degree angles, or one of each? You want to put 30 here and 30 here?
Yeah.
Oh, okay. Well, then the other ones must go on top and bottom. The 60-degree blocks, top and bottom. So that makes this angle, because remember, that's where our angles are actually located. That makes that angle add up to, well, 30 plus 60 is 90. So that is a 90-degree angle, making all of these 90-degree angles. Now the question is, are our opposite sides actually parallel? Well, I hope so. They should be. Because if I look here, this makes that C shape, right? Makes that C shape. So that means this angle and this angle this angle here are same side interior angles. Are those two angles supplementary? Yes. And since same side interior angles are supplementary, adding up to 180, that means absolutely 100% sure that this side is parallel to that side. And for the exact same reasons, we're going to get this side parallel to that side. Okay? Questions? All right, on the back side here, again, we have another proof. So let's see if we can figure this one out. We want to start out with our two columns. We're always setting up two column proofs here. Our first statement is actually a whole bunch of givens. We got three. I'm not going to be a stickler with you guys about saying in a plane. Okay, technically, yes, that needs to be there, but I'm not going to be a stickler on that. Okay? You just need to tell me that we know that C is perpendicular to B. We know that B is perpendicular to D. And we know that D is perpendicular to A. All of that is given. We are trying to prove that C is perpendicular to A. Okay? Now, first thing you got to remember is, of course, this arrowhead implies that this line is going to keep going. Okay? So it should intersect line A, but will it intersect at a right angle? I don't know. So we're going to have to work our way around here to see if we can find out that A and C are in fact perpendicular.
What about the transitive property?
Okay, the transitive property of parallel lines says that if we have parallel lines, we don't have parallel lines, we have perpendicular lines. So we definitely can't use the transitive property of parallel lines. Okay, but we might be able to say some lines are parallel. That's possible. That's possible. So looking at that, which lines, just without even trying to write the proof, which lines do you think are going to be parallel? A and B, C and D. I agree. Okay. Well, look back at your theorems on the front side. Don't we have a theorem in there that says something about lines being perpendicular to the same line? Yeah? Okay. So, what does it say?
If two lines are perpendicular to the same line,
If 2 lines are perpendicular to the same line, then they are parallel to each other. So, we know that C is perpendicular to B. We know that D is perpendicular to B. So what can we say? C is parallel to D. And what name did I give that theorem on the front side? Lines perpendicular to the same line theorem. Long name. Okay. Excellent. So we again know that we know that C is parallel to D. All right. We know that. Well, we might want to try to show that B and A are parallel. Well, for the same reason, then, can I say that B and A are parallel? Are those two lines perpendicular to the same line? Yeah, they're both perpendicular to D. So A is parallel to B, again, by lines perpendicular to the same line theorem. All right. Again, we're trying to prove that C is perpendicular to A. We know that A is parallel to B. Let's see, what else can we do? Let's highlight everything we know about our two lines we're trying to show are perpendicular. Sometimes just organizing our thoughts is the way to go. So we know that C is perpendicular to B. We know that A is parallel to B. Ooh, wait a minute. Does that help us here? Look back at your theorems. Say that again. Perpendicular transversal theorem says what? Can you remind me of that?
If a line is perpendicular to one of two parallel lines, and it is also perpendicular to the other.
If a line is perpendicular to one of two parallel lines, then it's perpendicular to the other. So C is perpendicular to B, which is one of these parallel lines. Therefore, it must be perpendicular to the other. So that's exactly what we want to say here. We can now say that C is perpendicular to A by the, and what do we call that? Perpendicular transversal theorem? Perpendicular transversal theorem. Oops. Okay, so as we've gone through and done our proof now, we're done. My question is, do we need step 2? Was that important information needed in our proof? No. To say that A was parallel to B, we only needed this, right? We needed that to say that A was parallel to B. We did not need to use that C was parallel to D at all. So that should not be in our proof. Now that we know it, we should go back and erase it so that we know that that is not a needed thing. Okay, for your notes, I would like you just to cross it out. But on a test or quiz or homework, if it's a step that's not actually needed in the proof, get rid of it. Okay, it is not a needed step. So there we have our complete proof. Questions? None yet? Okay. Let's go to the homework.